vaccination. I mean, I know that this talk was supposed to be nearly 2 months ago, but it turns out that the Swiss vaccination against the flu did not help against the British strain of the flu, so it had to be cancelled at short notice. So I hope that you will find the time, I mean, that I can give the specialized lectures, I mean, sometime next summer. So today, I mean, I just want to talk a little bit about my mathematical interests. So, I mean, as was already mentioned, I mean, I'm a number theorist. So, I mean, GAUS said that number theory is the queen of mathematics, as is well known, and I agree with that. And in this case, I mean, the Birch Swinnerton-Dyer conjecture is clearly one of the crown jewels. And that is what I want to talk about today. So what is number theory? Well, okay, if that works, then I could answer this. What is number theory? So, well, it is certainly one of the oldest subjects of mathematics. I mean, going back to the ancient Greeks. So, I mean, we study the properties, I mean, of the integers and the rational numbers. So, and in algebraic number theory particularly, we are interested in rational solutions of polynomial equations. So, I mean, here are some examples which are well known. So we have Pythagoras equation, I mean, x squared plus y squared is equal to z squared. And it is well known, I mean, that there are infinitely many, I mean, triples of positive rational numbers, I mean, x, y, and z, I mean, which satisfy that equation. And of course, it is well known, I mean, that Pythagoras, I mean, discovered, I mean, that the sides, I mean, of a right-angled triangle satisfy that equation. And I really like the story that when he discovered it, he was so excited that he ran into the temple and sacrificed them off. I mean, that is not something we do these days. So, well, another sort of similar, well, apparently related equation is Fermat's equation, where we just replace the exponents, I mean, by an integer greater or equal to 3. And even though it is sort of structurally very similar to Pythagoras' equation, I mean, it took many hundreds of years and many mathematicians, I mean, to establish that there are no positive rational numbers, x, y, and z, which satisfy that equation. So the general question is, I mean, given a polynomial with rational coefficients, say n variables, does it have solutions in the integers or the rational numbers? So let us first specialize two equations in two variables. I mean, it turns out that this case is already fairly complicated. So linear and quadratic equations are well understood, and in fact, they were already well understood 2000 years ago, thanks to the work of Diophantus of Alexandria. So the next case is where if we allow cubic exponents, and equations of this form are called elliptic curves. So we are looking at equations of the form y squared is equal to x cubed plus ax plus b, where a and b are rational numbers, which satisfy, I mean, this constraint, I mean, that 4a cubed plus 27b squared is not equal to 0. So, I mean, the idea is that if we draw the real graph of such an equation, it doesn't have cusps or self-intersections, I mean, thanks to this constraint. So the question is, I mean, what can we say about the rational solutions of such an equation? So about pairs of rational numbers, x and y, which satisfy this equation. So, I mean, there is, of course, a question, why should one care about this at all? Except it's the next easiest case, I mean, to what Diophantus already studied. Well, it turns out that these elliptic curves are sort of lurking in the background of many famous problems in number theory. So one example, a famous example, is Weyl's proof of Fermat's last theorem. I mean, the elliptic curves, I mean, play a very important role. But I want to talk about another motivating example, I mean, where sort of elliptic curves are sort of coming in, I mean, through the back door, namely the congruent number problem. So let's go back to Pythagoras' theorem and consider a Pythagorean triple. So a triple of positive rational numbers, ABC, which satisfy Pythagoras' equation and hence are the sides of a right-angled triangle. Okay. So what can we say about this triangle? Well, we can, for example, compute its area. So the area is a half AB. So the question is, which integers can arise in this way? So we make the following definition. A positive integer n is congruent if there exists a Pythagorean triple ABC such that the area of the corresponding triangle is equal to n. So in other words, n is congruent if there exist positive rational numbers ABC which simultaneously satisfy these two equations. So the challenge now is determine the congruent numbers. I mean, they can't be that hard, right? I mean, after all, we understand Pythagorean triples fairly well. Okay, well, let's look at some examples. Well, 6 is congruent. Well, that's obvious. I mean, from the first Pythagorean triple in nature, I mean, 3, 4, 5, I mean, the area of the triangle is equal to 6. That's fine. Well, 5 is congruent. That's already a little bit less obvious. But by trial and error, I mean, you might be lucky and, I mean, find this triangle. Well, and 127 is congruent. Well, I challenge you, I mean, to find that by trial and error. And it turns out, I mean, that this is really, there are infinitely many triangles with right-angled triangles with rational sides and area 127, and that is the smallest, the simplest one that you can find. So maybe it isn't that easy after all. I mean, to sort of say which numbers are congruent or not. So, I mean, this question of congruent numbers was first studied by the Persian mathematician Al-Karaji, so who lived about 1,000 years ago. So he made tables, I mean, which I mean, one can find pictures of on the internet, I mean, of congruent numbers. So then Fibonacci, I mean, studied the same question about 150 years later, and he proved the following theorem, or stated the following theorem in the Liber Quadratorum. So in the book of squares, namely that 5 and 7 are congruent numbers. And he stated, but did not prove, that 1 is not a congruent number. So in other words, he claimed that there exists no right-angled triangle with rational sides and area 1. Or, I mean, equivalently, where the area is a square, because we can always scale the triangle, I mean, to make the area equal to 1. Well, that proof is missing. Okay, so Fermat took up this challenge. So, and 500 years later, proved that 1 is not a congruent number. And in order to prove this, I mean, he used a very clever argument, I mean, called the descent algorithm, which we are going to see again and again, I mean, in this talk. Now, amusingly, I mean, this result of Fermat is very closely related to Fermat's last theorem, when the exponent is equal to 4. Namely, we have the following corollary. There are no positive integers x, y, and z which satisfy Fermat's equation, x to the 4 plus y to the 4 is equal to z to the 4. And the argument is extremely simple. We argue by contradiction. So suppose there exists such positive integers x, y, and z. Then we define numbers a, b, and c, I mean, in this way. And we check, I mean, that they satisfy Pythagoras' equation and that the area is a square. So, I mean, I find this an extremely neat application, I mean, of the fact that 1 is not a congruent number. And it is possible, I mean, that this corollary, I mean, sparked Fermat's interest, I mean, in the more general Fermat equation. Okay, so what else, I mean, is known about congruent numbers? Well, Monsky proved in the 1990s, I mean, some results about whether or not prime p is a congruent number. So very recently, I mean, Ye Tian, I mean, proved some results on congruent numbers with many prime factors. I mean, in the same spirit as Monsky's results. But it is an open question. Given n, does there exist a way of telling whether or not n is a congruent number? We do not know how to prove this. And here I'm lying a bit, actually. So there does exist an algorithm And it is built upon this descent algorithm that Fermat came up with, but we cannot prove that this algorithm will always finish. So it has worked so far in every example we have tried, but it is an open problem, and it is a very hard open problem to prove that this algorithm will always turn on. And this is related, I mean, to the Birch-Swinnerton-Dyer conjecture, and I will come back to that later. Okay, so that's a congruent number problem. It was a favorite problem of my old advisor. So the question is, what does it have to do with elliptic curves? Well, here's a theorem. So a positive integer n is congruent if and only if the elliptic curve y squared is equal to x cubed minus n squared x has a rational solution, so a pair of rational numbers x, y, which satisfy the equation with y not equal to 0. I mean, we observe, of course, if y is equal to 0, I mean, it's clear what the values of x are. It's plus minus n or equal to 0. Okay, so how do we prove this? Well, in some sense, one just does it. Okay, I mean, so if you have, I mean, right angle triangle with rational sides and area n, I mean, you can write down x and y. You will observe, I mean, that y is certainly not going to be equal to 0. And conversely, I mean, if you have rational numbers x and y with y not equal to 0, which satisfies the equation, I mean, then we can write down a Pythagorean triple with the right properties. Okay, so I hope that this convinces you that the question of studying rational points on elliptic curves is really something worthwhile thinking about. So let's have a closer look at elliptic curves. So suppose that we take an elliptic curve and we define the set of rational points on the elliptic curve to be the set of pairs of rational numbers x, y, which satisfy that equation. So, I mean, a priori, I mean, that's just a set that we don't know very much about. But it turns out that it has a really deep and interesting arithmetic structure. Namely, it has a structure of an abelian group. So one can describe this group structure, I mean, very nicely in geometric way. So suppose that we have two rational points, P and Q, then we take the line, I mean, through these 2 points. Because we're dealing with a cubic equation, it will intersect the graph of the elliptic curve and precisely one other point, which turns out to be rational, and we will reflect this point, I mean, in the x-axis, and this is the point P plus Q. So it turns out that that works. I mean, that gives an abelian group law. So to double a point, we just take the tangent, and the identity is just a point at infinity. So, I mean, r and minus r are just reflected points in the x-axis. Okay, that is already very interesting. But it turns out that even more is true. So this is the celebrated theorem of Mordell, namely that it is a finitely generated abelian group. And this is good news because finitely generated abelian groups are classified. So we know that the group of rational points on an elliptic curve is a direct product of a finite abelian group, the torsion subgroup, and a number of copies of the integers. So in this number of copies is an important invariant. It's called the rank of the elliptic curve. Okay, so in other words, attached to an elliptic curve, we have 2 important invariants, namely the torsion subgroup and the rank. But it turns out that one is much deeper than the other. So, I mean, the torsion subgroup is very well understood. I mean, it's the theorem of Mazur. I mean, I think there are 13 different possibilities. I mean, what the torsion subgroup can look like. But the rank is an extremely mysterious object. So for example, if we look at the elliptic curve, which comes from the congruent number problem, say y squared is x cubed minus n squared x. In this case, one can show that the torsion subgroup is precisely z modulo 2 squared. And it consists of the point of infinity and precisely those points where the y coordinate is equal to 0. In other words, precisely those points which do not contribute any triangles. So we can restate this result as that n is congruent if and only if this elliptic curve has positive rank. Okay, so this already shows you, I mean, that the rank is really important and deep invariant of an elliptic curve. So in particular, we can restate Fermat theorem as that the curve y squared is x cubed minus x has rank 0, because we know that 1 is not a congruent number. Well, let's look at some more examples where one can show, I mean, that for n equal to 26, I mean, the elliptic curve has rank 0, so 26 is not congruent. For n equal to 31, the elliptic curve can be shown to have rank 1. So 31 is congruent. And for n equal to 34, the elliptic curve has rank 2. So in some sense, 34 is very congruent. I mean, there are lots and lots of rational triangles. I mean, with rational sides and area 34. So what else is known about the rank? Well, Bhargava and his collaborators have shown that at least 83% of elliptic curves have rank 0 or 1. In fact, one expects that it's 100%. So elliptic curves, I mean, with higher rank should be extremely rare. I mean, in the set of all elliptic curves. But it is an open problem to find an algorithm known to finish which computes the rank of an elliptic curve. So we run into precisely the same problem. We have an algorithm, the descent algorithm. It has worked in every example we have tried, and we can't prove that it doesn't finish, that it finishes. So, and it turns out, I mean, that this question, I mean, of computing the rank of an elliptic curve is closely related, I mean, to an object from a totally different world. I mean, after all, I mean, elliptic curve, I mean, is sort of an algebraic object, just an algebraic equation. And it is related in some very mysterious ways, I mean, to an object called an L function, which lives, I mean, in the world of complex analysis. So let's look again at an elliptic curve and suppose that A and B are actually integers. We can always do that, I mean, just by sort of scaling up and clearing the denominators. Then for each prime P, we can look at the elliptic curve modulo P. So we just look at modulo P, I mean, of the coefficients. So, and it turns out that there is also a reduction map modulo P from the group of rational points on the elliptic curve to the group of FP points of the elliptic curve modulo P. So where FP is just a field with P elements. So suppose now that the elliptic curve has positive rank. So there are lots and lots of rational points. Then somehow one should expect, at least as P varies over all the primes, that should somehow be reflected, I mean, by the number of points under this, by the image of this reduction map. Yeah, so if there are lots and lots of rational points, then it should somehow be reflected in the number of points on E modulo P. So, yeah, so I mean, another way of saying it, the asymptotic behavior of the number of points on E modulo P should tell us something about the rank of the elliptic curve. So the first question to ask is, I mean, how large do we expect this number to be? Well, there is an easy heuristic, I mean, which says that the number of points on E modulo P is roughly equal to P plus 1. Yeah, and I mean, Hasse has shown that if we look at the difference between this expected number of points and the real number of points on E modulo P, then this difference is never too large. Namely, that the absolute value of this number AP is always less than 2 times the square root of P. So we're always fairly close, I mean, to the expected number. So remember now our expectation. If the rank of the elliptic curve is positive, then there should be a bias towards the number of points on E modulo P being large as P varies over all the prime numbers. So in other words, this number AP should be more often negative as P varies over all the prime numbers. So we now want to encode this information, this number AP and the prime P, in a complex analytic function. So we define the local L factor at P of the elliptic curve as the inverse of a polynomial in P to the minus S, so which just depends on these two values, P and AP. I mean, there are conceptual reasons, I mean, why this is a good function to consider, yeah, which I'm not going to talk about. So we now want to somehow reflect this expectation in the properties, I mean, of this function. But the first thing to notice is we only expect it asymptotically over all P. So it makes sense to define the L function of the elliptic curve as the infinite product of these local L factors. So where we have one factor for each prime P, which just depends on local data. Well, maybe this reminds you of the Riemann zeta function. Well spotted, I mean, that is not a coincidence. Okay. So, well, the first question for such an infinite product is, does it actually converge anywhere? Well, the answer is yes. I mean, it follows from Huss's inequality that the L function converges when the real part of S is greater than 3/2. So, and thanks to the work of Wiles and others, one can show that the L function has analytic continuation to all of the complex plane. Okay, now we remember our expectation. If the rank of the elliptic curve is large, then the L function should be small when the value of S is small. We will look at some examples. So, I mean, here we look again at the elliptic curves, I mean, coming from the congruent number problem, in the case when n is 26, 31, and 34. And you will remember that the ranks are 0, 1, and 2, respectively. So let's see what happens when we analytically continue. Well, you will notice something, right? Namely that something interesting happens at the point S equals 1. So for the elliptic curve, I mean, which has rank 0, the L function does not vanish at the point S equals 1. But for the two elliptic curves, I mean, of positive ranks, the L function does vanish at this point, and it vanishes to even and odd order. Yeah, and one can show, I mean, that the orders to which it vanishes are precisely 1 and 2. So what do we have? We have three elliptic curves of ranks 0, 1, and 2, respectively. And we have the L functions, which at the point S equals 1, have orders of vanishing 0, 1, and 2. Well, that is not a coincidence. That is the celebrated conjecture of Birch and Swinnerton-Dyer. So this conjecture was formulated in 1963, astonishingly on the basis of numerical experimentation. I mean, nowadays, yeah, I mean, thanks to these mathematical software packages, I mean, Sage and Magma and so on, everyone can check the DSC conjecture in explicit examples on their home laptop. At the time, there was a unique computer in Cambridge. And Birch and Swinnerton-Dyer had to apply for time, I mean, to actually be allowed, I mean, to run the experiments. And Birch actually told a very nice story. So they were allocated time during the night because mathematics was low on the list of priorities for using a computer. And there was a young female computer assistant, I mean, who helped them with the experiments. And Birch comments, we had a lot of time to get to know each other during these nights. We got married 2 years later. So, well, there you go. Well, that was not the only outcome of the experiments. I mean, they formulated the following conjecture, namely that the order of the L function at the point S equals 1 determines the rank of the elliptic curve. And even more, if you develop the L function as a Taylor series around the point S equals 1, then there is an explicit formula for the leading term in terms of the arithmetic invariance of the elliptic curve. And these arithmetic invariants involve a very mysterious group, I mean, the so-called Tate-Shafarevich group, which is closely related to the question of the descent algorithm for computing the rank finishing. Yeah. So I just want to say, I mean, this is such a beautiful conjecture because the L function really is only built up from local data, from the behavior of the elliptic curve modulo P, where P varies over all the primes. And what this here says is that the L function knows about the global arithmetic of the elliptic curve. And this is amazing. Yeah. Well, in any case, so I mean, that is a conjecture. So there are many generalizations. I mean, nowadays there's a huge network of conjectures, I mean, which generalize the BSD conjecture. So one can formulate it for elliptic curves defined over number fields. One can replace an elliptic curve by an abelian variety. But then there are also many other objects, I mean, which have L functions attached. So general algebraic varieties defined over Q or over a number field. And more generally, something called motives, which, well, no one really knows what a motive is, but one should think of it as a piece of the geometry of an algebraic variety. So the question is, can one formulate an analog of the BSD conjecture for these more general L functions? Or other is said in a different way, can we attach an arithmetic meaning to certain values of these L functions? So the answer is yes, at least conjecturally. So that was formulated by Spencer Bloch and Kazuya Kato in 1990. So they formulated the following conjecture. So given a motive M, if we look at the order of vanishing of the L function of the dual motive, then this should govern, then that should measure the size of a certain cohomology group, the so-called Selma group attached to the motive. So if the motive arises from an elliptic curve, then we almost gain, I mean, the Birch-Swinnerton-Dyer conjecture. So, and I mean, of course, you may ask what's special about the point S equals 1. Well, it isn't. I mean, you can twist, there's a notion of twisting a motive, I mean, by integers. So, and I mean, for this twisted motive, the conjecture, I mean, says something about the point S equal to 1 minus n. Okay, so it gives an arithmetic interpretation, I mean, to the values of the L function of the motive at the integer points in terms of the Selma group. And the Selma group, I mean, really is a generalization of the group of rational points on an elliptic. Okay, so I mean, that is the most general formulation, I mean, of this kind of conjecture. But let's go back, I mean, to the original Birch-Swinnerton-Dyer conjecture. So, I mean, the very first results, I mean, were proven by my old advisor, John Coates, together with his PhD student, I mean, Andrew Wiles. So in 1976, so namely they proved that E over Q being an elliptic curve with complex multiplication, which means it's a special kind of elliptic curve with lots and lots of symmetries, which they exploit. If the analytic rank, which we call the value of the L function, so if the value of the L function at S equals 1 is not equal to 0, then the Mordell-Weil group is finite. So the rank is equal to 0. Yeah, so let me just sort of say, I mean, that the elliptic curves that we have seen, I mean, coming from the congruent number problem, are elliptic curves with complex multiplication. So, okay, that's for elliptic curves with CM. What about the general case? Well, it's still open. Okay, so I mean, the strongest result in this direction, I mean, is due to Victor Kolyvagin. So who proved it when the order of vanishing is at most 1. So in this case, the order of vanishing determines the rank of the elliptic curve. And I just want to say, nothing is known when the order of vanishing is bigger than 1. That seems to be a genuinely difficult case, which cannot be cracked, I mean, by the methods that Kolyvagin and then others, I mean, introduced and refined. Okay, so I mean, what I briefly want to talk about is how does he prove it when the order of vanishing is equal to 0? Well, so the first step is to recall what's now the modularity theorem. At the time, it was the Taniyama-Shimura conjecture, later proved by Wiles, namely that motives of elliptic curves correspond to motives of certain modular forms. Now, what's a modular form? Well, a modular form is a complex analytic function defined on the complex upper half plane with lots and lots of symmetries. And these symmetries are illustrated, I mean, by this tessellation of the complex upper half plane. Well, maybe that looks familiar. In this case, you may be thinking of Escher's lizards, which tessellate the complex upper half plane, in a very similar way. Okay, so you can use this modularity theorem to replace elliptic curves, by modular forms. So in other words, it is sufficient to prove the Bloch-Kato conjecture in analytic rank 0, so when the L value does not vanish, for the motives of modular forms. Well, okay, that just means converting one hard problem into another hard problem. What have we gained? Well, the point is the following, namely, what Polyvagin does in order to prove the Bloch-Kato conjecture for motives attached to modular forms is to construct the first example of what's now called an Euler system, which is in some sense an arithmetic avatar of the L function of a modular form. I don't want to say precisely what it is. Roughly, it is an infinite collection, of geometric objects, which stand in certain relations to each other. And these relations are governed by the local L factors of the L function. So how does he construct this Euler system? Well, the point is the theory of Shimura varieties. So, these are varieties, which arise from the representation theory of matrix groups. And the study of these Shimura varieties is an entire industry in itself. They're extremely important in what's called the Langnans program. And it turns out that the motives of modular forms appear inside the Shimura variety attached to GL2. And the Shimura variety attached to GL2 has a special name. It's called a modular curve. And this means that Polyvagin could build this Euler system using tools from the representation theory of GL2. And this Euler system was then the key to proving the special cases of the Bloch-Kato conjecture that then implied the BSC conjecture in analytic rank 0. So the motivating question, for my research in the last, well, I don't really know how many years, probably at least 10, was can we imitate this? Can we build Euler systems for Shimura varieties attached to other groups than GL2? And before I say, what we have been able to do, let me just explain what such an Euler system would be good for. So, there is a generalization of modular forms, which are called automorphic forms. So they are in some sense the analog of modular forms for groups other than GL2. So, you may already have seen such an example. Say genus 2 Siegel modular forms are automorphic forms for the symplectic group GSP4. And similarly, the Hilbert modular forms, for GL2 over real quadratic fields, and so on. So automorphic forms give rise to motives, well, at least conjecturally. Sometimes it's known, sometimes it isn't. And there is a class of results, which are called modularity results, which says that many naturally occurring motives arise as motives attached to automorphic forms. So we have already seen one example, namely Weyl's modularity theorem is one example of such a modularity result, because it says motives of elliptic curves correspond to motives attached to modular forms. Well, there are very recent results, for elliptic curves over imaginary quadratic fields. So, Allen, Carey, and Thorne, and then, they proved some partial results, which were completed by Karayani and Newton. So they show, that the motives attached to those elliptic curves correspond, to motives attached to genus 2 Siegel modular forms. And there are some partial results by Boxer, Caligari, G, and Piloni, which says that motives attached to abelian surfaces arise also from motives of automorphic forms for the symplectic group GSP4. Okay, so suppose now that we have an Euler system for such a Shimura variety, and suppose it is non-trivial, and this is important, and I'll come back to this later. So suppose we have a non-trivial Euler system, then we can use, a very well-established tool, due to Kato and Rubin, so namely which says such an Euler system has applications to the Bloch-Kato conjecture for the automorphic forms attached to that Shimura variety. Okay, so that's called the Euler system machine. And then using modularity, we can translate it into applications to the Birch-Swinnerton-Dyer conjecture. So in other words, Euler systems are extremely powerful tools for attacking, the BSD conjecture, or more generally, the Bloch-Kato conjecture. Just a pity that they're very hard to construct. Until about 9 years ago, there were precisely 4 examples of Euler systems. Okay. So, well, in 2014, together with Antonio Ley and David Löffler, we constructed a new Euler system. So for the Shimura variety of GL2 times GL2. So in some sense, it was still of a fairly easy case, right? And so because it's just a product of 2 groups, which we understood fairly well. So we were able to prove it's non-trivial. And together with Guido Kings, we proved the following result. So let f and g be modular forms, and let n be an integer in the critical range. Well, I don't really want to say what critical range is. It's a certain range of integers determined, by f and g. So if the value of the L function of the product of the 2 modular forms at the value s equals n does not vanish, then the Bloch-Kato conjecture holds for the tensor product of the motives twisted by n. Okay, so I'll explain in a moment, so roughly, how we prove this. But let me just say, using modularity, we obtain applications to something called the equivariant Birch-Swinnerton-Dyer conjecture for elliptic curves in analytic rank 0. So extending previous work of Bertolini, Damon, and Roger. So equivariant, well, for the experts, it means we take an elliptic curve over Q and we twist it by a 2-dimensional odd-Artin representation. One can formulate, a variant of BSD for that, and so, this follows, from our result. Okay, so how do we prove this? Well, step 1, clearly construction of the Euler system. Well, this is fundamentally a geometric construction. Okay, it uses tools, from smooth representation theory of the underlying group GL2 times GL2. So then we prove what's called an explicit reciprocity law. So what's that? Well, it gives a relation between the Euler system and this value of the L function that we are after. Because we want some result. If the value of the L function isn't 0, then we can use the Euler system, to deduce cases of the Bloch-Kato conjecture. So in other words, it gives us a way of showing or of establishing a criterion that the Euler system is non-trivial. Okay, so this is what such an explicit reciprocity law is for. So the tools for proving that are totally different from those, that we use for constructing the Euler system. So, they use tools, from periodic Hodge theory, periodic geometry, periodic analysis, and so on. So once we have these 2 steps, we deduce if the value of the L function is non-zero, the Euler system is non-trivial. Well, that's obvious, once we have step 2. And then we can use the Euler system machine to say, well, we have now a non-trivial Euler system. So the Selmer group is equal to 0. So that's fine. So the hard steps are steps 1 and 2. And I again want to emphasize, we really need step 2, because otherwise we can't rule out that we have constructed the 0 Euler system, which is useful for nothing at all. Okay. So, okay, so that's the story of that Euler system. So to our great surprise, our construction of the Euler system generalized, and it generalized hugely. So, for example, in 2018, with Ley and Löffler, and our construction was later refined by my student Giada Grossi, we constructed an Euler system for GL2 over F, where F is a real quadratic field. With Skinner, David and I constructed an Euler system for GSP4 and an Euler system for the group GU21. So then one of our Arizona project groups, constructed an Euler system for GSP4 times GL2. And my former student, Andy Graham, together with Shrenik Shah, constructed an infinite family of Euler systems, generalizing Colli-Wagen's original construction. So that is the case for n equals 1. And there's just a few. The list goes on. So the question, does that now mean that we can prove cases of the Bloch-Kato conjecture in huge generality? Well, that would be nice, wouldn't it? But there is a problem. We need to know that the Euler systems are non-zero. And that turned out to be a major headache. Yeah, there is a general strategy, for proving an explicit reciprocity law. So, remember, explicit reciprocity law relates on the one side, the Euler system, with values of the L function on the other side. And there is a strategy, namely to use an intermediate object, which is called a p-adic L function. So that strategy was introduced by Bertolini, Damon, and Prasanna. So p-adic L function is somewhere in between, the complex analytic world and the geometric world, where the Euler system lives. Now, in the case of GL2 times GL2, we were able, to carry out that strategy. But the reason was that the underlying Shimura variety was really simple. It was just a product of two modular curves. In none of the other cases, none, where we could construct Euler systems, could we even carry out the first step, namely the construction of the p-adic L function. Let alone, prove an explicit reciprocity law. And we were in the frustrating situation. We had all these new Euler systems, and we couldn't show that a single one of them was in zero. So we were stuck at that, for quite a long time. So, more precisely, we were stuck from 2015 until November 2017. What happened in November 2017, I'll tell you in a moment. So, but we tried really, really hard, to solve this problem. Sometimes when I think back to this time, it reminds me of a quote from this wonderful book, 3 Men in a Boat, by Jerome K. Jerome. So where the 3 men try and open a tin of pineapples without a tin opener. So the quote goes as follows: "We beat it out flat, we beat it back square, we battered it into every shape known to geometry, but we could not make a hole in it." Well, yes, I know the feeling. So the story continues as follows. There was one great dent across the top of the tin that had the appearance of a mocking grin, and it drove us furious, and we flung the tin far into the river. And trust me, we were very, very close, to that point on many occasions. But then a miracle happened. Namely, beginning of November 2017, we attended a conference in Princeton where Vincent Piloni gave a talk on higher Heda theory. And we realized within seconds, for me, I'm a bit slower, it took me a bit longer, but we realized very quickly that that was the missing piece for constructing the p-adic L function we were after. So basically, after the talk, we went to Piloni and said, listen, we need to talk. So we completed the construction, together with Piloni and Skinner, so of a p-adic L function for genus 2 Siegel modular forms in 2019. And well, it was clear that we then had the tools for proving the explicit reciprocity law for the Euler system for GSP4. But it took us, another year. So, to prove this explicit reciprocity law. And apart from higher Heda theory, it uses many, many tools, from all over mathematics. So, just to list a few, we use rigid geometry, we use various p-adic cohomology theories, symptomic cohomology, log symptomic cohomology. So we use the theory of p-adic integration, as introduced by Coleman and generalized by Amnon Besser. We use Iwasawa theory, we use p-adic Hodge theory, a la Fontaine and Perrin-Riou, and many other ingredients. Yeah, so, but I mean, in the end, we got there. And then we could finally harvest the fruits from our Euler system. So, I mean, to begin with, I mean, we could prove, I mean, the Bloch-Kato conjecture in analytic rank 0. So when the value of the L function does not vanish for the critical twists of genus 2 Siegel modular forms. So that was already quite nice. And then we can combine it, I mean, with the modularity results. I mean, we sort of say, I mean, that the motifs, I mean, attached to genus 2 Siegel modular, for certain genus 2 Siegel modular forms correspond to the motifs of elliptic curves over imaginary quadratic fields. So there we go. We proved this last year. So assuming some technical hypotheses, the BSD conjecture in analytic rank 0 holds for modular elliptic curves over imaginary quadratic fields and for modular abelian surfaces. So there we go. So, I mean, I think it took us in total about 8 years, I mean, to get to that result. So, I mean, let me just end by saying, I mean, I think, so, I mean, this Dyer-Hilger theory, I mean, which was the key, I mean, which we used, I mean, in proving this result or proving the explicit reciprocity law. I mean, this is now known in great generality, or at least a variant, I mean, which is called Coleman theory, I mean, thanks to the work of Boxer and Filoni. And we now believe, I mean, that the methods we have introduced, I mean, both for constructing periodic L functions and for proving explicit reciprocity laws are applicable in great generality. I mean, we have several members of our research groups, I mean, working on that. I mean, we are currently, so David and I are working with Giada Grossi, I mean, on the case of the Euler system for GL2 over real quadratic fields. So we hope, I mean, that there will be many more cases of the Bloch-Kato conjecture known in analytic rank 0 in the near future. Thank you.